This next section uses the linearization of a function, the tangent line, a lot. So I'm going to start you off with a warm-up question of just finding the linearization of the function x cubed minus 3x minus 1 at the point where x equals -3. So pause the video, give this a shot, and come back. So your derivative should be 3x squared minus 1. And the two things that we're going to need to find are f of -3 and then f prime of -3. And then put those into our tangent line equation. F of -3 would be equal to -3 cubed minus 3 times -3 minus 1. -3 cubed would be -27 minus 3 times -3. That would be like plus 9, the negatives cancel, and then minus 1. So this would be, let's see, 27 minus 9 is 18, plus 1 would be 19, so this would be -19. F of -3 would be 3 times positive 9, so that would be 27 minus 3, so that one's a lot easier. That's going to be 24. And then our linearization, L of x, you might remember that the formula for that would be f of a plus f prime of a times x minus a. And this would be very similar to like what you would do if you did like the y minus y0 equals m times x minus x0, and then just bring that y0 over. It would give you the same old thing. So for us, L of x is f of -3, which is, -19, plus f prime of -3, which is 24, times x minus -3. So that's what it is, and if you wanted to simplify that, you could. So this is like 24x plus 24 times 3 is 72 minus 19. And those combine to be 53. So that's our formula for L of x. So Newton's method is basically a way to use the tangent line to approximate solutions of an equation. So let's consider that same function, x cubed minus 3x minus 1. And let's say that we want to solve the equation x cubed minus 3x minus 1 equals 0. So that we're just setting that function equal to 0, right? Graphically, if we were to plot or sketch a graph of this guy, I don't know exactly what it would look like, but it would be maybe something like this. We would basically be trying to, if we're setting this thing equal to 0, we're really looking for like the x-intercept. So we're looking for when does this guy cross the x-axis, all right? And so what we're going to do is use the tangent line at x equals -3 to approximate this. So here will be -3, and then I'm just going to draw like a really zoomed in picture of like what might be happening there. So this is the point that we are looking for. And if we're starting with x equals -3, the idea is we're going to, we'll draw the tangent line. And then we will basically say, well, the tangent line is really close to the graph of this function. So if we were to use the graph of the tangent line, we could estimate where it's going to cross the x-axis by just saying, so we can estimate this point over here by finding where our tangent line crosses the x-axis. So this right here would just be an approximation of our actual solution to this equation over here. So that's the idea. And as you can kind of tell, like this, you know, depending on like what our guess is and what our actual solution is, like this first approximation like might not be very good. And so what you can do to deal with that would be to take this a step further. So think of -3 as like our first guess for the solution. So, you know, maybe, all right, so like x cubed, if I were to plug in -3, okay, what I meant to say, or what I'm sort of thinking in my head, maybe like -2 would be a better guess. So if I were to plug in -2 here, I'd get like -8 plus 6 minus 1. So this would be, that's not even close to 0. So basically what I'm sort of trying to do in my head right now is say like, all right, so I want to come up with a guess for a solution to this equation. And maybe this guess would be like pretty close to a solution. So, I mean, if I were to plug in -3 or -2, it's not going to be like that close to spitting out a 0 here. So it's not really giving me exactly what I wanted, but whatever. The point is, this guess right here is going to be closer than this original first guess. And so we use this as then our second guess, and then we then go to that point on the graph, and then we can do the same thing. We can just sketch, we can just like draw the tangent line over here and use this tangent line to get a new approximation. And this new approximation will be hopefully even closer to our actual solution. And maybe we're still not satisfied with this, so we can just keep on, you know, zooming in and just picking new points to approximate the tangent line to this thing with. And so you're just going to like very quickly get closer and closer and closer to the actual answer. Okay, so let's actually see how this would work in this example. So before we found the equation of the tangent line was this. All right, so here's our tangent line at x equals -3. So we want to know, when is this guy equal to 0? So all we have to do is set this equal to 0 and then solve for x. So then x, we can bring that -53 over and then divide by 24 on both sides. So x would be -53 over 24. That's like about -2.5. So -2.5 would be our like next guess for like a solution, and then we can find the tangent line at -2.5 or whatever this number is, and then figure out when that tangent line crosses the x-axis and so on. All right, so in general, we're not going to actually compute the tangent line every single time. There's a quicker way to do this, and so I'm going to show you how. So our general formula for the tangent line is L of x equals f of a plus f prime of a times x minus a. And so if we are setting this equal to 0, then we can just solve for x. So if we do this, we can just bring that f of a over to the other side, and then divide by f prime of a, and then I don't need these parentheses anymore. And then to finish solving for x, I just bring this -a to the other side by adding a on both sides. So x would be equal to a minus f of a over f prime of a. And so if we start with an initial guess x1, then our next, our x2 would be like our next approximation. So our initial guess x1 is like just a guess approximation, think of it like that. And then x2 would be our next approximation. And then we would think of x1, our first guess, as being our a value, and x2 as being like the place where we're going to cross the x-axis. That's the thing that we're solving for. So x2 would be our original guess, x1, minus f of x1 over f prime of x1. And so doing what we did in the previous slide, where we set the equation of the tangent line equal to 0 after finding the equation of the tangent line, and then kind of going from there. That's going to do the exact same thing as just like using this little formula right here. So then your next guess, x3, would be you take your previous guess and then subtract f of your previous guess over f prime of your previous guess. And in general, xn plus 1 is going to be equal to xn minus f of xn over f prime of xn. And so, yeah, this is we can just use this now. All right, so let's do an example. Let's find the approximations x2 and x3 to a solution of x to the fourth plus 2x minus 8 equals 0 with an initial guess of x1 equals 1. All right, so we start with this. Our f of x is just going to be what's on the left side of the equation. If this is not a 0 on the right side of the equation, if this was like a 5 or something like that, just bring it to the other side, just like subtract it over so that your right hand side is like becomes a 0. But anyway, if your right hand side is a 0, then your f of x is just going to be whatever on the left. And then f prime here will be 4x cubed plus 2. And so if we start with x1 equals 1, then x2 is going to be equal to 1 minus f of 1 over f prime of 1, which is equal to 1 minus, and f of 1 is going to be 1 to the fourth plus 2 times 1 minus 8, and then f prime of 1 is going to be 4 times 1 cubed plus 2. So this is equal to 1 minus, and then we'll get negative 5 in the numerator and 6 in the denominator, so 1 and 5/6, which you could write alternatively as 11 over 6. So this is our x2. x2 is going to be 11/6. x3 is going to be that previous x value, or that previous approximation, 11/6, and then minus f of 11 over 6 over f prime of 11 over 6. So you can tell these approximations start getting like pretty tedious pretty fast, and so in practice this is kind of like a good thing to sort of hand to a computer. So a computer system will often use Newton's method or a version of Newton's method to approximate solutions. That's kind of like one thing that this could be used for. It's very much a computational thing. Anyway, f of 11 over 6 would be 11 over 6 to the fourth plus 2 times 11 over 6 minus 8 all over 4 times 11 over 6 cubed plus 2. This is like my third time having to do this video because I've had to like restart for stupid reasons every time. So I'm pretty sure just going off of memory, plugging it into my calculator, I end up getting like about 1.57-ish. That might be wrong. I'm literally just going off of memory, but it doesn't really matter too much anyway. So we start with a guess of like 1, and then 1 and 5/6 or 11/6 is about like 1.83. And so what's happening here is we're starting at 1. Our next approximation is like 1.83, and then our next approximation goes down to like 1.57. So we go up a lot and then we go down a little bit. So it's kind of like we're like maybe you would hope that like it would do something like this, like it goes up and like overshoots, and then it goes down, it overshoots a little bit, and maybe it goes like down again and then down again and then up again and then down and then maybe up, whatever. So you might hope that it would just like sort of hone into a solution. All right, let's now use Newton's method to approximate a solution to x to the fourth equals 3. All right, so you might think that our function f of x should be x to the fourth, but this 3 is on the right-hand side, so we actually want our right-hand side to always be a 0, so we should write this as an equation where our right-hand side is equal to 0 first. And so our f of x would actually be x to the fourth minus 3. Then f prime of x will just be 4x cubed. And then we can kind of go from here. So this is not giving us an initial guess or even like how many approximations to do. We just kind of have to use our best judgment here. So what would be like a good guess for a good first guess to just start with for x to the fourth equals 3? Well, you know, maybe we can start with 1. If we started with 1, well, 1 to the fourth is definitely not equal to 3. But if I were to do x1 equals 2, then 2 to the fourth, 2, 4, 8, 16. 16 is like way further from 3 than 1 is, right? So if I needed to pick a whole number, x1 equals 1 would probably be like a pretty reasonable first guess. So we'll do that. x2 is then going to be, so it's going to be 1 minus f of 1 over f prime of 1. So this is equal to f of 1 is 1 minus 3, which is negative 2. And f prime of 1 is 4 times 1 cubed. So this is basically just 1.5. Okay. Oops. All right, so then x2 is equal to 1.5. I'll just write it as 3 halves. x3 would then be equal to 3 halves minus f of 3 halves over f prime of 3 halves. So this is 3 halves minus f of 3 halves is 3 halves to the fourth minus 3 over 4 times 3 halves cubed. Okay, and so, oof, give me 1 second. I'm going to need my calculator for this one. All right, so we get 3 halves minus that over that. All right, so I'm getting about 1.347, and then a bunch of 2's. Copy that, bring that over. So x2 was like 1.3472. And if we're wondering how accurate our approximation is, well, if like the actual solution to this, so if you were to solve for x here, you would just take the fourth root of both sides. So take the fourth root of 3. Then the fourth root of 3 is roughly equal. It is equal to 1.31607. And so, you know, it's accurate to the first 2 decimals, and then the next couple ones not so much, but like we've only done like 2 iterations of this approximation thing, right? Was I saying x2? Yeah, I should have said x3, right? This was x sub 3. X sub 1 was our first guess. X sub 2 was our first approximation, and then x sub 3 was our second approximation. All right. So presumably, if we were to like kind of keep going, maybe x4 would be like 1.316. I don't know, 525. I'm just making up numbers right now. But it might be like might be agreeing with this number up to like a couple more decimals or something like that. You might hope. Maybe it does, maybe it doesn't. You'd actually have to just kind of run through it and find out. All right. I'll let you try this one. So pause the video and try to find an approximation, just the x2 approximation to this equation with an initial guess of x1 equals -2. So pause the video and then come back to this. All right. I probably should have mentioned before I told you to pause and try it. You will probably find like something kind of goes wrong with this one, and that's okay. All right, so if x1 is equal to -2, then what would x sub 2 be equal to? So it's equal, it would just be our previous x value minus f of -2 over f prime of -2. So this is equal to -2 minus, and then what's f of -2? Be -8 plus 3 times -2 squared, which is +4, and then plus 5, all over f prime of -2, which would be 3 times 4 plus 6 times -2. So we get -2 minus, was that 12? 4, the 9 up top, and then this is like 12 minus 12, so we get like a 0 on the bottom. So this is immediately bad because we're dividing by 0 right here. So this is a problem. All right, so what's going on here? So obviously this is like undefined, like this just like does not work in this case. And so why does this not work? All right, well, what we ended up doing was basically using f prime of 2 for our denominator. And if f prime of 2, or -2, ended up being, well, this was like 12 minus 12, which is 0. So f prime of -2 is equal to 0. What does that tell us about our tangent line? So our tangent line is f of -2, which was, what do we say that was? That was 9, plus our slope, which was 0, times x minus -2. This is like the equation of our tangent line. So our tangent line is literally just always equal to 9. Graphically, what does that mean? That means that, so here is -2, and then here would be 9. Oops. Here would be 9. This means that we have, so if f prime is equal to 0 at this point, that means the slope of our tangent line is 0. So this is just a straight horizontal line. So what is this Newton's method really doing? So it is basically saying you take the approximation of your curve, which is the tangent line. So you take the tangent line, and then you figure out where does the tangent line cross the x-axis. And this is just a horizontal line, so because the slope is equal to 0, this tangent line is never going to cross the x-axis. So you just literally can't like solve for a place where this guy crosses the x-axis, which is what this formula is doing. It's solving for a place where the tangent line crosses the x-axis. And because that slope is 0, then that's just not going to exist. So this problem was basically just written to be flawed, to just highlight that if your slope is 0, then you just straight up cannot do this because of that geometry. All right. Well, here's something that you actually can do. So try this self-check question. Using Newton's method with an initial guess of x1 equals 2, just find the second approximation, x sub 2, of the square root of 3. As a hint to this, just remember that the square root of 3 is a root of the polynomial x squared minus 3. All right, so take a minute, pause the video, come back with an answer, with a guess, and we'll go over. All right, so really what we're trying to solve, the equation x squared minus 3 equals 0. So our f of x is x squared minus 3, and our f prime of x is equal to 2x. Okay. Why is this what we're doing? Well, because if we're looking for, like, what is the actual solution to this? Well, we're starting with, like, okay, what number squared is equal to 3? Well, the square root of 3 is, right? So if x is equal to square root of 3, then x squared is equal to 3, so x squared minus 3 is equal to 0. And now we can do Newton's method on this equation with this being our function, this being our derivative, and x1 equals 2 being our first guess. Then x2 is going to be equal to previous thing minus f of previous thing over f prime of previous thing. So 2 minus, what's f of 2? That's going to be 2 squared minus 3, so 4 minus 3, which is 1. And then f prime of 2 is just 2 times 2, that's just 4. So this is 2 minus 1 over 4, which is equal to like 1 3/4. And 1 3/4 is just the same as 7/4. So our answer should be B, 7/4. Okay. Example 4. Let's find the approximation x sub 4 to a solution of sine of x equals x squared with an initial guess of x1 equals 1. All right. So again, we don't have a 0 on the right side of our equation, so we're going to bring the x squared over. So our f of x would be equal to sine of x minus x squared. Our f prime of x would be equal to cosine of x minus 2x. And then our x sub 2 would be equal to, let me write down my x sub 1. I just like to be organized this way. Helps my thoughts. X sub 2 is going to be equal to the previous thing minus f of previous thing over f prime of previous thing. It's equal to 1 minus f of 1, which is sine of 1 minus 1 squared, over f prime of 1, which is cosine of 1 minus 2 times 1. All right, well, what's this equal to? So, what is sine of 1, right? So you would have to, like, do what? So there's a problem here, right? So sine of 1, I have no idea what that's equal to without, like, using a calculator. So if I need to use a calculator to do, like, this estimation, then, like, what the heck am I even doing? Because I could just use a calculator to estimate, like, this thing in the first place. So, like, the whole point of, like, approximating solutions is, like, we either don't want to use a calculator, or maybe we are just, like, programming a computer to, like, be the calculator. And so, like, this sort of relies on the ability to compute easily all of the things in this formula. So if you're not really able to easily compute, like, sine of 1 or cosine of 1, without using, like, a different calculator, which is just going to also be approximating things, then, you know, that's going to create problems. And then, like, when we start doing, like, x3, you know, this number is, like, already terrible, and so, like, x3 is going to be even worse, and then x4 is just going to be, like, exponentially worse. So this is another sort of problem that can kind of pop up here. Okay. Pretty much the rest of this section is just going to be problems. Because it turns out Newton's method is it's a good way to approximate things, But like because it has a lot of flaws, it really is best served as like an initial method to approximate things that can be built on to create even better ways of approximating things. So Newton's method is, think of it as like a first step towards like better approximation things. And so here's another thing that could sort of go wrong and that you might want to avoid with like your approximation methods. So let's find an approximation to a solution of this thing with an initial guess of x1 equals 0. So this is our f of x, and then our f prime of x would be negative 3x squared plus 8x minus 2. So x1 equals 0, x2 is equal to 0 minus f of 0 over f prime of 0. That's equal to 0 minus, all right, this is our f of x, right? So f of 0 would be this stuff would all go away, and then we're just left with 2. And then f prime of 0 would be equal to, well, all of these terms would go away, and we're just left with negative 2. Boop. So we get 0 minus 2 over negative 2. So that's just equal to positive 2 over 2, which is just 1. Great. So then our x2 is equal to 1. And so what would our x3 be equal to? It's going to be equal to 1 minus f of 1 over f prime of 1. That is equal to 1 minus, all right, what is f of 1? So I would get negative 1 cubed plus 4 times 1 squared minus 2 times 1 plus 2 all over f prime of 1, which would be negative 3 plus 8 minus 2. How does this simplify? All right, so let's see. These 2's cancel, and the top becomes just 3. What happens on the bottom? This is 8 minus 5. So 8 minus 5 is just 3. So we get 1 minus 3 over 3, which is 1 minus 1, and 1 minus 1 is 0. So x3 is equal to 0. What would our x4 then be? All right, well, our x1 was 0, our x2 was 1, our x3 was 0. You might notice that there's a pattern emerging. So x4 is going to be 0 minus f of 0 over f prime of 0. And we literally already did that calculation. It's right up here. It's just going to give us 1 again. Okay, so x4 is just going to be equal to 1. And then you can, like, you know, you can even right away say like what x5 would be. x5 would be just like 1 minus f of 1 over f prime of 1, which would end up equaling 0. So x5 would be 0, x6 would be 1, x7 would be 0. And so these things are just like cycling, 0, 1, 0, 1, 0, 1. So you could have like this cycling behavior. And so this is never going to just like land on like a set approximation. It's not going to be getting any closer to like some fixed number or anything like that. Like it's just not going to happen. Okay, so to summarize all like the possible disadvantages. So this one I haven't really discussed too much, but maybe intuitively you can understand that our approximation depends heavily on the choice of our x1. So, you know, if we were to make our first guess be x sub 1 equals like 5 versus making it 17 or 105, like that will drastically modify our process and how accurate our results are and how quickly our results will give us something accurate. You could have that the slope is equal to 0, in which case your tangent line is just never going to cross the x-axis and you won't be able to find a solution. The values of your approximations could cycle, like they could be, oh shoot, this was supposed to be, this is a typo, ignore this, this is going to be on like the next bullet point. Sorry about that. So this was like for the previous example that we did where it's cycling between 0 and 1. It could also cycle between like 1, 2, and 3, or 4, 5, and 6, or 1, 7, and -2, and 13, whatever, just any number of numbers. It could just kind of cycle through them in some repeating pattern. And the values of your approximations, they are not guaranteed to converge. This is where this was supposed to go. Pretend that this went on to this slide right here. Yeah, so if you were to estimate a solution to arctangent of x equals 0, I forget this. I forget how this works out. I don't remember if this depends so much on your initial guess. I think it doesn't depend on your initial guess, but I might be wrong. But the point is, for some initial guess, if you were to approximate a solution to arctangent of x equals 0, which is not a hard thing to solve algebraically, like if you were to just like do this like in a trig class, you could just do it very quickly. The approximations to this solution would just like very quickly like jump off to like infinity. Like they just like would not converge to like any specific number. So there's like no guarantee that it's like even this method is going to give you something super like approximate. So the whole point of this section is not so much that Newton's method is a great way of approximating things, but rather what you should take away from this section is this is a way of approximating things. This is like a first taste at like what approximations of like solutions to equations sort of looks like and how they can sort of be used, and what sort of flaws like might pop up in a given approximation method, and like how you might want to like avoid these flaws, like when you're using something, or things to sort of be aware of when you're using these approximations or whatever. So anyway, that's it for that section. Thank you for listening.